So hi, welcome back. We are entering our final part in this session. This is a part 4. We are going to discuss about the pulmonary function test and the alveolar ventilation. So the pulmonary function tests, these are again going to be used in helping diagnose patient to differentiate between the obstructive versus restrictive lung disease and also to monitor about their progress. Okay. One thing that can be measured is the vital capacity, or more specifically, we call it the forced vital capacity, which is the maximal volume of air that can be exhaled after the maximal inspiration. We already talked about before when you're going to completely fill the lung and then see how much air that you can get out so that you get down only the one things left, that residual volume. Then there's another thing that can be measured, which is how much you can expire in 1 second. So completely fill our lung and then see how quickly you can get the air out. So how much it gets out in a second. So if you take the ratio of these two numbers, how much you can get out in a second versus how much you can get out over an unlimited period of time, in the normal individuals, the number should be approximately about 80%. So you should be able to get 80% of the air out of the normal lung in 1 second. Of the air that you're going to be able to get off your lung, this will exclude the residual volume. So in our two type of the disease, state that this number are going to change. It should be somewhat predictable that someone with obstructive lung disease, where they have a problem getting their air out, then this ratio is going to be less than 80%. They're going to get less than 80% of their air out of their lung in 1 second. Their vital capacity, their forced vital capacity is somewhat going to be normal in the obstructive lung disease. In restrictive lung disease, where they have a problem getting the air in, they have no problem getting the air out. So their FEV1 to FVC ratio should be normal. They should be able to get 80% of their air out in 1 second. However, it's the actual number of those two parameters that should be different because their vital capacity is smaller. That means in the actual number, the volume of their FEV1 will also be smaller. So the ratio can be normal, but they have a reduced vital capacity in restrictive lung disease. So we're going to see in the next slide if we can see the pattern of the respiratory disease. Here is the normal graph, and then it's the obstructive and the restrictive. Okay. So in the normal person, at the first in the test, the patient or the subject is told to be breathing normally. Okay, they just breathing in, breathing out normally, and then in this point, and they told, okay, inhale as much as you can, and that's right here, increasing the volume, and then they hold in this point, okay, just breathe out, push out that air as fast as you can. So this here in when they exhale. So after 1 second, it should be 80% of their volume is just forced to exhale. Okay, so they have just a little bit left of the air after 1 second. So their forced vital capacity is normal, and FEV1 is also normal. So when someone have obstructive lung disease such as emphysema, they're breathing with their lung is, more inflated, just like a compensation mechanism to their disease. So they take a normal breath, you know, okay, and then they just told up to fill up your lung, and then they told just, okay, now you exhale as much as you can, all right, as quickly as you can. And then you can see that when they're pushing out the air, that you can see after 1 second they only got a small amount of air that can be exhaled. Okay, so that's going to be typical in obstructive lung disease. they have so many seconds after 1 second to just exhale all the 80% of the air. In the restrictive lung disease, you can see that they have a problem to inhale. So there is a smaller volume when they told to be inhale as much as they can, but they have no problem to just exhale quickly as they can. So the FEV1 80% is still normal. After 1 second, 80% of the air can be exhaled. But they can but you can see about the really small amount of the number, the only 2 liters rather than the 3 liters about the normal person. So so if you look at the actual volume that are being measured, they're both being smaller, but the ratio is still 80%. So the FVC is decreased, but the ratio is still normal. Okay, now we're going to talk about the importance of the alveolar ventilation. We already discussed about the minute ventilation in the previous part. So this is one thing that very important. So when we are breathing, we are not completely replacing the air in our lung, not even close. You know that the volume of the air in the lung is 3 liters, right? So let's say the tidal volume is 5 mils or half liters. And when we just bring this volume into the lung, you have to remember that we have an anatomical dead space, right? In the conducting zone. It's about 150 mils of air. So we only have 350 mils that going to the part of the respiratory system. Is approximately of 10% of the air in the lung. So that's important thing keep in your mind. We only replacing a small portion of our air when breathing in normal like this, and that's a lot of what we are doing is just filling the conducting volume. So in the normal person, the alveolar ventilation is really, really important because the alveolar ventilation is just giving you the reflection how much is fresh air to bring in your lung and really give you fresh air in your body. Okay, so how can we know that for sure? So that means that we have really to consider how much that conducting volume is, which is also the same thing that we are going to refer as a dead space, right? So we already talk about the minute ventilation is. That's going to be how much air you're bringing into the respiratory system in each minute. We're going to calculate it using the tidal volume multiplied by the respiratory rate, right? The minute ventilation is tidal volume multiplied by respiratory rate. Okay, we got 3 different scenario right here. Okay, this is a tidal volume and this is a respiratory rate. All right. However, we now that we really need to consider alveolar ventilation because of the anatomical dead space, because we really care about is how much fresh air is getting into the alveoli, not getting in the respiratory system. So to calculate that, we are going to take the tidal volume and subtract the volume of the dead space. In each case, is going to assume the dead space is 150 cc or 150 mils. Okay. If we do that for scenario 1, in here, when someone is respiratory rate is 50, just very, very fast, something like venting, and venting and hyperventilate. And then in every case of the respiratory rate is only bringing in 100 milliliters. It's basically like they're panting, and so in that case they're only bringing 100 mils per minute. They not even feeling, you remember that the dead space is 150. They're not even feeling their conducting space or dead space. So that is 0 liters of this air is getting into the alveoli. So the alveolar ventilation is 0. If we have someone that has really normal breathing pattern of 10 breath per minute, and every time the tidal volume is 500, and the air ventilation, it should be 500 minus 150, which is 350, and multiply by 10 is going to be 3,500 milliliters. Then if we have someone that is breathing only 5 times a minute but taking a deeper breath and give you a large tidal volume, it will get you much more higher alveolar ventilation. So we can have the same minute ventilation here, but if we are taking deeper, less frequent breaths, they have a radically different alveolar and ventilation. So it is important to keep in mind that minute ventilation does not necessarily means all that much. We care more about the alveolar ventilation as also very important to consider. So this why you cannot be hyperventilating when you panic attack. When you're hyperventilating, there's nothing fresh air comes into your body. So if you get stressed, hyperventilating, you just calm down and then breathing up more deeply and more less frequent. This is also a problem when you have a patient with a very high respiratory rate. In one point, if it's longer for a long time, there's no fresh air inside their body. So this is going to be a problem. Okay. Okay, now we're going to need now about the volume that getting into the lungs that also very influenced by the partial pressure. We also know that from the environment, the air is just contained from different gases, right? That's we are going to be considering where we know that most of the air that we breathe is going to be nitrogen. It's only 20% is oxygen. And that in the air we breathe, carbon dioxide is very low. We also know that the total pressure is going to be made up of the sum of the partial pressures of the gases. That means that the pressure of oxygen is going to be equal to the fraction of inspired air that oxygen times the atmospheric pressure. So since oxygen is 21% of the atmosphere and the atmosphere pressure is 760, that means in the normal air that we are breathing, the pressure of oxygen is 160 mils of mercury. Remember that I said that one of the roles of conducting system is to moisturize air. So that means that we are adding with water vapor form of water. The vapor pressure of water is 47 millimeter of mercury. So that has to be subtract from 760 of the pressure of atmospheric air to calculate what the pressure of oxygen will be in inspired air. It is 150 millimeter of mercury. Okay, so that is the number, the pressure of oxygen in the air once it has entered into the respiratory system before it is diluted by the air that's already in there. So that's what we are going to start considering. So this is what we just calculated, right? We're going to say that we know the pressure of oxygen in the atmosphere is 160. Exactly. Once it gets humidified, it's going to become a 150 of mercury. We've already said that the pressure of CO2 in the atmosphere is very low. Once we get the alveoli, so we get the PA, right? The PA, the P capital A, pressure in the alveoli. The pressure of oxygen is going to be much lower. And that's going to be because remember, we said that fresh air is going to be diluted. We're not going to completely replace the air in the lungs. So it's going to get diluted by the old air. The old air is having the oxygen taken out of it continually by the blood. So why the pressure from the atmosphere will be decreased in the alveoli? For the CO2, we have a different issue where CO2 is constantly being put into diffusing into the lung. That means that the pressure of CO2 in the alveoli um, is going to be much greater than the almost negligible pressure of CO2 in air that's coming in. Then once we look at the pressure of oxygen that is dissolved in the R3, this is a capital A, right? This is the A, so this is R3. Okay. Uh, so you can see that the pressure in the artery is basically matching almost exactly pressure in the alveoli. So in the alveoli it's 105 and the artery is 100 millimeter mercury. The same things occur also in the carbon dioxide. So we're getting basically complete equilibration between the alveoli and the arteries. That means that the pressure of gas in the alveoli is going to be what is going to determine the pressure of oxygen in the blood. Alveoli and the blood. Okay. The arterial blood is going to be taken to the organs where the organs take the oxygen and dump CO2. So you'll see the pressure in veins of oxygen will be decreased because the oxygen is just being used by the organs, but the organ dumps the CO2, so the pressure in the vein CO2 will be increased from 40 to 46 millimeter mercury. So this is our key concept. We already talked about the ventilation. We've talked about the minute ventilation. On now we also consider about the alveolar ventilation. So how much fresh air is getting to the alveoli because that's what matters. We've also talked about how that means you're going to have to consider dead space when we get anatomical dead space, which is the only kind of dead space we've considered so far, which is just the conducting zone of the respiratory tract. Later, we will consider a little bit areas of the lungs that are not well ventilated or perfused, which is also going to be included when we talk about the physiological dead space that's going to occur in even normal lungs when we don't have perfect ventilation or perfusion in different areas. So that's all for the part 4, and see you in the next session.